Okay, hello everyone. In a new video. In this one we are going to explain chapter 5, which is the chapter of electric power and energy, and the second unit of electricity. Let me start by section number 1, which is introducing the electric power. So the electric power across an electric component is given by so the electric power, which is denoted by P, capital P stands for power, is given by the product of the voltage and the electric current. So this is the electric power. So for example, consider here that we have an electric component independent of the nature of this electric component. And suppose that the voltage across this electric component is given by U, for example, say 12 volts, and the traverse current, which is I, is equal to 1 amperes. Then we can calculate the electric power, which is given by P is equal to U multiplied by I. So the value of U is 12 and the value of I is 1, and this will give us 12. Since U is in the SI, which is volts, and I is in the SI, which is amperes, so the value of P will be in the SI, which is given by watts. So the unit of the electric power in the SI is watts, and its symbol is given by capital W. Then let me write here where P is the electric power of unit. The symbol of its unit is capital W, which stands for watts, and U is the voltage. Its symbol is V, which stands for volts. And as for the electric current, I is the electric current. And the symbol of its unit is capital A, which stands for amperes. And we know that in physics, for any formula or equation that consists of triplet, we can construct its triangle, which is given by this. Here, because we have multiply, then P will be at the top and U and I at the bottom. So for example, if you are interested in calculating the value of I, then I is given by P divided by U. And if you are interested in calculating the value of, say for example, U, putting our hand over U, then U will be given by P divided by capital I. So let me write the following note. Now, because P and U are living on different floors, so P at the top and U at the bottom, then we say that P and U are directly proportional. Then when U increases, then we have that I increases. And because also P and I live on different floors, so P and I are said to be directly proportional. And this means that when I increases, then when I increases, sorry, here, let me write P increases. P increases. And this is because they are directly proportional. Now let me move to the next section, which is section number 2, and it is given by the electric power across a resistor. We know now that the electric power denoted by P across any electric component, I repeat, across any electric component independent of its nature, is given by the product of the voltage and the electric current. This stands for any electric component. Now suppose that this electric component is given by a resistor of resistance R. So we know that because this electric component is a resistor, we can apply Ohm's law to it. Then let's consider, so let me say here that P is equal to UI, this is the first form of the electric power. Now P is equal to U times I. We know that across a resistor we can apply Ohm's law, which is given by U is equal to R times I. This is given by Ohm's law. Then notice that here we can replace U in the electric power by U is equal to R times I. So we have that P is equal to U multiplied by I, and we can replace the value of U by R multiplied by I, and since we are replacing, we don't forget the brackets. So what I have done here, I have replaced the value of U in the electric power by Ohm's law. Now, because this expression is a combination of multiplications, so we can get rid of the brackets, and it will be R multiplied by I multiplied by I, which is given by Ri square. So P is equal to Ri square is the second form of the electric power, and this only holds across a resistor. Now there is also another form. So let me say that P is equal to U times I, and here between the brackets let me apply Ohm's law. U is equal to Ri, and this is given by Ohm's law. And here from Ohm's law, if you construct the triangle of this formula, so U at the top and R and I at the bottom, then I can be written as U divided by R. Let me write it here. And now instead of replacing the value of U by Ri, let me replace the value of I, which is Ohm's law, U divided by R. Then P is equal to U multiplied by I, and we replace I by Ohm's law, which is given by U divided by R. Now, because this expression here is a combination between multiplications and divisions, so we can get rid of the brackets, and it's given by U times U divided by R. So here U is divided by 1. Now recall that whenever we have A over B multiplied by C over D, this will give us A multiplied by C divided by B multiplied by D. So it's given by U multiplied by U divided by 1 multiplied by R, which is equal to U square over R. So P is equal to U square over R is the third form of the electric power. So now what do we conclude? We conclude that the electric power has 3 different forms, and they are given by P is equal to U times I. This is the first form. And the second form is given by P is equal to U square divided by R. Sorry. P is equal to Ri square. And the third form is given by P is equal to U squared divided by R. So what's the common and the difference between these three different forms? For example, if they gave me the voltage and the current, so for sure we will use the first form, because this form is an explicit relation between the voltage and the current. If they gave me the resistance and the current, we will use the second form. And if they gave me the voltage and the resistor, we will use the third form. Notice that these two forms, they only hold for a resistor. Okay, and the first form is a general form for any electric component. So these two, we use them only across a resistor, and we cannot use them before we prove them, as we shall see later in the coming exercises. So now, in order for the ideas to be clear, let's solve some exercises as a direct application. So here in exercise number 1, they are telling me calculate the power consumed by the resistor R if the voltage across it is 0.12 kilovolts. So we know that kilovolts is not the SI unit of voltage. In order to convert from kilovolt to volt, we multiply by 1000. So it's 0.12 multiplied by 1000. This will give us 120 volts. So the voltage U is equal to 120 volts. And the current traversing this resistor is given by, and the current traversing it is 150 milliamps. And we know that milliamps is not the SI unit of electric current. In order to convert from milliamps to amps, we divide by 1000. So 150 divided by 1000, this will give us 0.15 amperes. Then I is equal to 0.15 amperes. Now here, because they are telling us to calculate the electric power consumed by the resistor R, so the electric component is a resistor, then we have three forms of electric powers, and they are given by P is equal to U multiplied by I, P is equal to Ri square, and P is equal to U square divided by R. So which one we will use? This depends on the given. They gave me the voltage and the current, so we will use the first form because we don't know the resistance. Then P is equal to U multiplied by I. Now replacing the value of U, which is given by 120, and replacing the value of I, which is given by 0.15. Now because I in the SI and U is in the SI, so the value of P will be in the SI, which is watts. Plugging this on the calculator will give us 18, so P is equal to 18 watts. Then the power consumed by this resistor is given by P is equal to 18 watts. Now in exercise number 2, they are telling me given a resistor R of resistance R is equal to 100 ohms. Now in number 1, they are telling me show that for a resistor we have P is equal to Ri square. So in other words, they are telling me to prove this relation across a resistor. Then in order to prove this, we will always start by the general form, which is given by P is equal to U multiplied by I. Then notice that here in this form, P is equal to Ri square, the resistance R appear in the equation. So this gives us a hint that we need to use Ohm's law, which is given by U is equal to Ri, Ohm's law. Moreover, the voltage doesn't appear, which means that we need to get rid of the voltage. So replacing U by R multiplied by I, and getting rid of the brackets, this will give us Ri square. Then in other words, we have proved that P is equal to Ri square. Now in number 2, they are telling me calculate the power consumed by the resistor of the current traversing it. I is equal to 0.5 amperes. So we have the resistance R and we have the electric current I, and they are telling me to calculate the power. Then we will use this form because we have the resistance and we have the electric current. Then P is equal to Ri square, replacing the value of R, which is given by 100, and the value of I, which is given by 0.5 to the power 2. Now plugging this on the calculator will give us 25. Because R in the SI and I is in the SI, so the value of P will be in the SI, which is 25 watts. So the value of P is equal to 25 watts. Now in number 3, they are telling me show that for a resistor we have P is equal to U square over R. So we need to prove that P is equal to U square over R, and this can be done by starting from the general form, which is given by P is equal to U multiplied by I. And because R appears in the equation, this gives us a hint that we need to apply Ohm's law to replace the value of I, because I doesn't appear in the equation. Then U is equal to R multiplied by I. This is given by Ohm's law. Now we need to replace the value of I because I doesn't appear in the equation. So I is equal to U divided by R. So U multiplied by U divided by R. Getting rid of the brackets. So this will be equal to U squared divided by R. So P is given by P is equal to U squared over R. Now in number 4, they are telling me calculate the power consumed by the resistor if the applied voltage is 20 volt. So they gave me the voltage to be 20 volts, and we already know the value of the resistance, which is 100 ohms. Then we need to calculate the value of P using this form. So P is equal to U squared divided by R, which is equal to 20 to the power 2 divided by 100. Plugging this on the calculator will give us 4. Since U is in the SI and R in the SI, the value of P will be in the SI, which is watts. So P is equal to 4 watts. Now in exercise number 3, they are telling me given a resistor of resistance R is equal to 150 ohms. In number 1, they are telling me show that for a resistor we have P is equal to Ri square and P is equal to U square over R. So we need to prove the two other forms of the electric power, starting from P is equal to U multiplied by I. Let's first start by proving P is equal to Ri square. So in order to prove this relation, we will start by P is equal to U multiplied by I. Now notice that here the resistance R appear in the equation, and we need to get rid of U, and this can be done using Ohm's law. We can apply Ohm's law because the given electric component is a resistor R. Then U is equal to Ri. Getting rid of U or replacing U by I multiplied by I, and getting rid of the brackets, this will give us Ri square. Then P is equal to Ri square. Now as for the second form, which is given by, or the third form, P is equal to U squared divided by R, we will follow the same steps. So starting from P is equal to U multiplied by I, here let me write Ohm's law. So U is equal to Ri, which is given by Ohm's law. And here, because I doesn't appear in the equation, then we need to replace the value of I in this form. So let me write here I is equal to U divided by R. So P is equal to U multiplied by U divided by R, which is equal to U multiplied by U divided by R, which is equal to U square over R. So P is equal to U square divided by R. This is the third form of the electric power. So here let me write P is equal to Ri square and P is equal to U square over R. Now in number 3 they are telling number 2, sorry. In number 2 they are telling me calculate the current traversing the resistor if the applied voltage is 12 volt. So we know that the voltage is given by 12 volt and already the resistance is given to be 150 ohms. So we need to find the current traversing this resistor, and this can be done using Ohm's law. Then apply Ohm's law to R. Then U is equal to R multiplied by I, constructing the triangle of this formula. U at the top, R and I at the bottom. We are interested in calculating the value of I. So I is equal to U divided by R. The value of U is 12. The value of R is 150. So plugging this on the calculator will give us 0.08. Since U is in the SI and R in the SI, so the value of I will be in the SI, which is amperes. And now in number 3, they are telling me calculate the applied voltage. We need to calculate the voltage. If the traverse current I is equal to 0.5 amperes, and we know that the resistance of this resistor is given by 150 amperes, this can be done by using Ohm's law. So always in physics, whenever we apply the law, we need to mention the law that we are using. Apply Ohm's law to R. Then U is equal to Ri, constructing the triangle of this formula. U at the top, R and I at the bottom. We are interested, no need to construct the triangle because already this is the form that we need, because we need to calculate the voltage. 150 multiplied by 0.5. Plugging this on the calculator will give us 75. Since R in the SI and I in the SI, so the value of U will be in the SI, which is voltages. Then U is equal to 75 volts. And now in exercise number 4, they are telling me a lamp L carrying the following inscription: 6 watt 12 volt is assumed as a resistor ohmic conductor of resistance R. So notice that till this moment they didn't mention anything about document 1, so we are not allowed to use it. So we have a lamp L carrying the following inscriptions: 6 watts and 12 volts. So what does each of them represent? Watts is the unit of power, so this is electric power. And V, volts, is the unit of voltages, so this is the voltage. So these inscriptions hold whenever the lamp L is functioning normally, yet we don't know the lamp L is functioning normally. And they told me that we can assume that this lamp is a resistor, an ohmic conductor, so we can apply Ohm's law to it, and its resistance is given by R. So it has a resistance R. So these are, for example, the inscriptions or the properties of the lamp L. Number 1. They are telling me in number 1, show that the current carried by the lamp while normal functioning is I0 is equal to 0.5 amperes. They told me while normal functioning. So here we are assuming that the lamp L is functioning normally. We know the electric power and we know the voltage. So we can calculate the current knowing that P is equal to U times I. Notice that here no need to mention any law because this is not a law unlike Ohm's law. Constructing the triangle of this formula, P at the top, U and I at the bottom. We are interested in calculating the value of I, which is given by I is equal to P divided by U. Now here the electric current is denoted by I0. So the value of P from the inscriptions, this is the value of P because it carries the unit W, which is watts. Dividing it by 12, which is the voltage, will give us 0.5. This is in the SI and this is in the SI, so the value of I0 will be in the SI, which is amperes. So what does I0 represent? I0 represents the electric current under normal functioning. Then we can add this to the inscription here. So when the lamp L functions normally, it will be traversed by a current which is equal to the rated current, which is 0.5 amperes. Now in number 2, they are telling me calculate R. So we need to calculate the resistance R, and for sure this can be done using ohms. Apply Ohm's law to L. Notice that in part 2 they didn't tell me that the lamp L is functioning normally. No need here for mentioning that the lamp L is functioning normally, because we can use the indications in two cases: either if the lamp L is functioning normally, or if we are calculating the resistance R, which is this case. So here I repeat that we can use the indications, although they didn't mention that the lamp L is functioning normally, because we are calculating resistance. For example, we cannot use these quantities, say for example 12 volt in law of addition of voltages, unless they mention it's functioning normally. Then U is equal to Ri, which is Ohm's law, constructing the triangle of this formula. U at the top, R and I at the bottom. We are interested in calculating the value of R, which is denoted by small r. U divided by I0, the electric current is denoted by I0 in this case. So 12 divided by 0.5 will give us 24. Since U is in the SI and I0 is in the SI, so the value of R will be in the SI, which is ohms. So R is equal to 24 ohms. Let me write here that the resistance R is equal to 24 ohms. All of these analyses are done to the lamp L, and yet L is not connected to any electric circuit. Now in number 3 they are telling me the lamp L is placed in an electric circuit as shown in the below document, document 1. They mentioned the document, so now we can use it. The resistors R1 and R2 have resistances. R1 is equal to 10 ohms and R2 is equal to 20 ohms. Let me make some space. Okay, the ammeter A of negligible resistance displays 0.1 amperes. So let's check which electric current does the ammeter reads. So notice that this electric circuit is a closed circuit. Then it delivers an electric current given by I in the main branch. So this is the main electric current. This is also a main branch. So this is the electric current I. This is the electric current I. This is the electric current I. Notice that at this point, the electric current splits into two currents given by I1 and I2. So this is not a main branch, this is a sub-branch traversed by the current I1. And this is traversed by the current I2. And at this point, both currents I1 and I2 join back to give me the electric current I. So the electric current that passes through the ammeter is given by I1, so the value of I1 is given by 0.1 amperes. So the value of I1 is equal to 0.1 amperes. Now 3.1, they are telling me calculate the value of the voltage U1 across R1. So we know the resistance of R1 to be 10 ohms, and we know the electric current traversing it, which is I1 is equal to 0.1 amperes. Then we can calculate its voltage using Ohm's law. So we are applying Ohm's law. Apply Ohm's law. To R1. This law is given by U is equal to R multiplied by I. So this is the form that we need. Let's label some stuff. U1, R1, I1. So the value of R1 is 10. The value of I1 is 0.1. Plugging this on the calculator will give us 1. Since R1 in the SI and I1 in the SI, so the value of U1 will be in the SI, which is U1 is equal to 1 volts. And I repeat, the trick in solving such type of exercises is to write the voltages, the applied voltage and the traverse current on the electric circuit itself. So this is 1 volts. Now in 3.2, they are telling me show that the current I2 carried by R2 is 0.05 amperes. So we need to determine the value of the current I2 traversed by R2. So we know the value of R2 to be 20 ohms. If we know the voltage across R2, we can determine the value of I2 using Ohm's law. Then let's say apply Ohm's law to R2. And the law is given by U is equal to R multiplied by I, constructing the triangle of this formula. U at the top, R and I at the bottom. Then I2 is given by U2 divided by R2. Notice that here the applied voltage across R1 is given by 1 volts, but because the ammeter is of negligible resistance, so we can consider that the ammeter is simply a connecting wire like this. Now in this case R1 and R2 are in parallels, so according to the law of uniqueness of voltages, they have the same voltage. So the value of I2 in this case is given by 1 because it's connected in parallel with R1 and the ammeter A is considered as a connecting wire. The value of R2 is given by 20. Plugging this on the calculator will give us 0.05. Since U is in the SI and the value of R in the SI, so the value of I will be in the SI, which is amperes. So I2 is equal to 0.05 amperes. Now in 3.3 they are telling me deduce the current I through the lamp L, and by deduce means that we need to use the part just previously before. In 3.2 we have determined the current I2, and from the reading of the ammeter we know the value of I1, so by applying law of addition of currents we can determine the value of I. Apply law of addition of currents. So how do we apply this law? Always on the left we will write the main current delivered by the battery, which is given by I, and on the right we will write the sum of different electric currents, and they are given by I1 plus I2. We are interested in calculating the value of I, so I is equal to the value of I1, which is given by 0.1, and the value of I2, which is given by 0.05. This will give us 0.15 amperes. So the value of I is equal to 0.15 amperes. Then now we know the traverse current through the lamp L. Now in 3.4 they are telling me does L function normally in this circuit? Why? In order to know whether the lamp L functions normally or no, we need to compare either the applied voltage or the traverse current with the rated inscriptions. So here in this case we have the traverse current and we have the rated current. Notice that the traverse current is given by 0.15 amperes, which is less than the rated current, which is 0.5 amperes. Therefore the lamp L will not function or function weakly. Since the traverse current is less than the rated current of the lamp L, and this is because 0.15 amperes is less than 0.5 amperes, then the lamp L will not function or function weakly. So that's it for me in this video, guys. In the next one we'll complete the explanation of this chapter.